Welcome to Lesson 6.1 Multi-GPU Training. Overview. You have two NVIDIA Tesla P40s sitting in your machine, 24 gigabytes of VRAM each. Right now, most training setups only touch one of them. This lesson changes that. Multi-GPU training can cut your fine-tuning time nearly in half, and you're going to understand exactly why, not just copy-paste a config and hope for the best. This is a 90-minute advanced lesson, and by the end you'll have both GPUs pulling their weight. Learning objectives. Here's what you'll walk away with. You'll understand the real difference between data parallel and distributed data parallel, when to use each, and why one is faster. You'll configure Unsloth to train across both Tesla P40s, dial in your batch sizes for maximum throughput, and monitor GPU utilization so you can actually verify it's working. You'll also know how to diagnose the most common multi-GPU failures on Windows. The target: 2 to 3 times faster training than a single GPU. Multi-GPU strategies. The simpler of the two strategies is data parallel. Think of GPU 0 as the foreman on a construction site. It takes the incoming batch of data, splits it into equal chunks, and hands each chunk to an available GPU. GPU 1 receives its slice, runs the forward pass, computes gradients on the backward pass, and ships those gradients back to GPU 0. The foreman then aggregates everything, updates the model weights, and the cycle repeats. The elegance here is simplicity. PyTorch wraps this entire workflow in a single function call. The trade-off is that GPU 0 carries extra overhead. It's doing the splitting, the aggregating, and the weight update, while GPU 1 only handles its portion of the compute. That asymmetry is exactly why data parallel tops out around 1.6 to 1.8 times speed up with two GPUs, rather than a clean 2x. Data parallel's strengths are real. It works on Windows without special configuration and requires almost no code changes. Literally one line wraps your model. The weakness is that GPU 0 bottleneck. It handles more work than GPU 1 every single step, which caps your efficiency. With two P40s, you can expect roughly 1.6 to 1.8 times the throughput of a single GPU. That's still a meaningful gain, and for most use cases it's the right starting point. Distributed data parallel, DDP, eliminates the foreman bottleneck entirely. Instead of one master process coordinating everything, each GPU runs its own independent. GPU 0 and GPU 1 each receive their own batch, each run their own forward and backward passes simultaneously, and then, crucially, they synchronize gradients through an operation called all-reduce before updating weights. No single GPU is doing extra administrative work. Both are computing at full capacity, then briefly communicating to stay in sync. That symmetry is why DDP achieves closer to a true 2x speedup, roughly 2.0 to 2.3 times with two GPUs. The cost is complexity. DDP requires launching multiple processes and has some rough edges on Windows that data parallel doesn't. DDP's profile is maximum efficiency with maximum complexity. It scales cleanly to many GPUs, and the speedup is the best you'll get from data parallelism. The friction points on Windows are real. The NCCL communication backend that DDP prefers was designed for Linux, and you'll need to work around it. You'll also launch your training differently. Not a single Python script, but a spawn multiprocess job. With two P40s, expect 2.0 to 2.3 times single GPU throughput when it's configured correctly. Method Uno, simple data parallel, easiest. Here's the data parallel setup from start to finish. The first block loads your model and token error through Unsloth's fast language model, with 4-bit quantization enabled to keep memory usage manageable across both GPUs. Then LoRa is applied. The R LoRa_alpha and LoRa underscore dropout parameters control how aggressively the model adapts during fine-tuning. Nothing unusual here compared to single GPU training. The multi-GPU piece, the code calls torch.cuda.device underscore countxc and prints the name of every GPU it finds. What you want to see is two devices listed, both Tesla P40S. If you only see one, stop and check your CUDA underscore visible underscore devices environment variable before going further. Once two GPUs are confirmed, the model is wrapped with torch.nn.data parallel. That single call is the entire multi-GPU configuration. From this point forward, every batch you feed the model will be automatically split across both GPUs. The printout confirming model ready for multi-GPU training is your green light to proceed. With the model wrapped, training setup follows the familiar unsloth pattern, but with a few deliberate choices for multi-GPU. The datasets are loaded from JSON and formatted using get_chat_template, which structures the inputs consistently for instruction tuning. Notice the per_device_train_batch_size is set to 8. That word per_device is doing real work here. With data parallel and two GPUs, each GPU processes 8 samples simultaneously. This is one of the primary ways multi-GPU training accelerates convergence. You're processing twice the data in the same wall clock time. The SFT trainer receives the model tokenizer and both datasets, then training is launched with trainer.train patney. When it completes, the model and tokenizer are saved. The output messages during training will show your loss and evaluation metrics. Watch that the loss curve behaves normally. A sudden spike or NAN values would indicate a batch size that's too aggressive for available memory. Method 2. Distributed data parallel, maximum speed. DDP requires launching multiple processes, one per GPU, rather than running a single Python script. On Windows, the cleanest way to do this is with torch.multiprocess. You'll write a dedicated training script called train_ddp.py that handles the multiprocess coordination. The train_ddp.py script has two key functions. Setup_ddp initializes the distributed process group. It sets master_addr and master_pot as environment variables, so all processes know where to rendezvous. Every process that calls this function joins the same training group. Inside train_ddp, each GPU process independently loads the model and tokenizer, applies LoRa, and then wraps the model with distributed data parallel. Notice the local _rank parameter threading through the function. This is how each process knows which physical GPU it owns. Process 0 uses GPU 0, process 1 uses GPU 1. The training arguments include local _rank in the output directory path, so each process writes to its own location without collisions. The main function detects how many GPUs are available and uses mp.spawn to launch one training process per GPU. mp.spawn handles the process lifecycle. It starts them, passes each one its rank, and cleans up when training finishes. You'll see output from both processes interleaved in the terminal, which is normal. Batch size optimization for multi-GPU. Effective batch size is the number that actually governs how your model learns. It's what the optimizer sees, not what any single GPU sees. The formula is straightforward. Multiply per_device_batch_size by num_GPUs, then multiply that by gradient_accumulation. Each factor serves a distinct purpose. Per device batch size is constrained by VRAM, how much fits on one GPU. Number of GPUs multiplies your throughput. Gradient accumulation lets you simulate a larger batch without increasing memory by running several forward-backward passes before each weight update. Understanding this formula means you can hit any target effective batch size even when VRAM is the limiting factor. A few concrete examples ground this. A single GPU with batch size 4 and 2 gradient accumulation steps gives you an effective batch of 8. Switch to 2 GPUs with data parallel or DDP, batch size 8 and no accumulation, you're at 16. Push the per device batch to 12 across 2 GPUs and you reach 24 per step. For your 2 Tesla P40S, the sweet spot is a per device batch size of 8 or 10. That balances VRAM headroom against throughput. You'll verify the exact ceiling in the next section with a binary search function. Rather than guessing your maximum batch size, this function finds it empirically. Find underscore max underscore batch underscore size runs a binary search between 1 and 32, testing whether the model can complete a forward pass at each candidate size without running out of memory. At each iteration, it selects a midpoint batch size, tokenizes a subset of your actual training data, and attempts a forward pass. If it succeeds, that size becomes the new lower bound, and the search continues upward. If a CUDA out-of-memory error fires, the upper bound drops. The search converges on the largest batch size your GPU can handle in roughly log2 32 5 iterations, rather than trial and error. The final print statement gives you the number to plug directly into per underscore device underscore train underscore batch underscore size. Run this once before committing to a training configuration and you'll never waste time babysitting a job that crashes at step 3. Monitoring multi-GPU usage. This PowerShell monitoring script runs NVIDIA dasami in a loop, refreshing every 2 seconds and clearing the terminal between updates so you're always looking at current data. The cyan header confirms the monitor is running. What you're watching for: both GPUs should show utilization above 80% during active training. Memory usage should be substantial on both devices, not just GPU 0. If you see GPU 0 pinned at 98% while GPU 1 sits at 5%, your data parallel wrapper isn't distributing work correctly, or the batch size is too small to make distribution worthwhile. That's your signal to investigate before running a full training job. Here's what a problem looks like in NVIDIA ZASMI output. GPU 0, the Tesla P40, is at 98% utilization with most of its 24 GB in use. It's working hard. GPU 1 is at 5% with almost no memory allocated. That's not a healthy multi-GPU run. Both GPUs should be well above 80% utilization and consuming comparable amounts of VRAM. This specific pattern, one GPU saturated, one idle, usually means one of 3 things. Data parallel wasn't applied. The batch size is so small that the overhead of splitting it isn't worth it. Or CUDA underscore visible underscore devices is hiding GPU 1 from PyTorch. The troubleshooting section covers all 3 fixes. For finer grained monitoring during training, the GPU monitor class runs on a background thread so it doesn't block your training loop. Every 5 seconds it polls torch.cuda.memory underscore allocated and torch.cuda.memory underscore reserved for each GPU, along with the utilization percentage from NVIDIA DMLPy. The value of this over NVIDIA SMI is that the output is time-stamped and integrated into your training logs. When you review a run later, you can correlate memory spikes with specific training steps rather than trying to remember what the terminal showed at hour 2. Instantiate GPU monitor before trainer .train_, call stopnf finally block, and you have automatic GPU telemetry for every training run. Troubleshooting multi-GPU issues. The most common symptom when multi-GPU training isn't working. NVIDIA SAMI shows GPU 0 active and GPU 1 doing nothing. Here's how to diagnose it systematically. This diagnostic code does 3 things in sequence. First, torch.coder.device_count_asa confirms how many GPUs PyTorch can see. The assertion on the next line fails fast if only one GPU is visible. Better to catch this immediately than discover it after a 20-minute warm-up. Second, it checks whether CUDA_visible_devices is set in your environment. This variable, if present, restricts which GPUs PyTorch can access. A value of 0 inches means GPU 1 is invisible to your process regardless of what NVIDIA SMI shows. If it's set, either unset it or change it to 0, 1 inch. Third, if both GPUs are confirmed visible, the model is wrapped with data parallel and the device_IDs list is printed. You want to see 0, 1 in that output. If you see only, the device count check fails silently somewhere upstream. Walk back through these 3 checks in order and the problem will surface. When you hit a CUDA out of memory error during multi-GPU training, the fix usually involves one or more of these adjustments. Reduce per_train_batch_size from 8 down to 6 or 4. Increase gradient_accumulation_steps. Reduce max_sake_length from 2048 to 1024. This cuts activation memory roughly in half. Gradient checkpointing should already be enabled through unsloth, but verify it's on if memory. These training arguments represent a conservative but stable multi-GPU configuration. Per device batch size of 4 keeps each GPU's activation memory well within the P40's 24 GB. Gradient accumulation steps of 2 brings the effective batch size back to 16, the same as the more aggressive 8 per device setting, but with half the peak memory footprint per step. Gradient checkpointing trades a small amount of compute for a significant reduction in memory. Instead of storing all intermediate activations during the forward pass, it recomputes them as needed during the backward pass. For large models, this can free several gigabytes per GPU. max_grad_norm of 1.0 clips gradients before they can destabilize training, a standard safeguard that costs nothing in practice. DDP on Windows has a specific failure mode worth knowing about. The NCCL backend, which is the default and fastest option for GPU to GPU communication, was built primarily for Linux. On Windows, it either fails to initialize or behaves unreliably. The fix is to use the glue backend instead. This updated setup_DDP function passes backend glue to dist.init_process_group instead of NCCL. Glue is PyTorch's cross-platform communication backend. It's slower than NCCL on Linux. The init master env dalamenda tells the process group to read master_addr and master_par from environment variables, which you set in the outer setup_world_size is the total number of processes, 1 per GPU, and rank is this processor's unique identifier. When this function returns without error, your distributed group is initialized and the processes can communicate during the all-reduced gradient sync. If glue DDP still gives you trouble on your specific Windows configuration, data parallel remains a valid fallback. You give up roughly 0.4 times the speedup compared to DDP, but you gain a setup that works reliably on Windows without process group configuration. For 2P40S, 1.7 times speedup is still a substantial reduction in training time. A different symptom, NVIDIA shows GPU 0 at 100% and GPU 1 at around 60%. This isn't a configuration error, it's the expected data parallel. GPU 0 is handling compute plus the batch splitting and gradient aggregation overhead, so it saturates first. GPU 1 finishes its compute share and then waits. This imbalance is inherent to data parallel's architecture. If this utilization gap bothers you, switching to DDP eliminates it. If 1.7 times speed up meets your needs, the imbalance is acceptable. Your training is still faster than single GPU. This single line is the DDP equivalent of the data parallel wrapper, but the mechanics are fundamentally different. With distributed data parallel, each process owns one GPU and wraps its own copy of the model. The device underscore IDs list contains just one entry, the local underscore rank of this process. There's no master GPU aggregating results. Instead, during the backward pass, DDP automatically triggers an all reduce operation across all processes, averaging the gradients so every GPU's model stays synchronized. The result is that both GPUs spend nearly all their time on compute rather than coordination overhead, which is why DDP achieves closer to a true 2x speedup. Performance benchmarking. This benchmarking script gives you hard numbers for your specific hardware rather than theoretical estimates. It runs a fixed number of training steps, 100 by default, and measures wall clock time. For single GPU runs, the model loads directly onto CUDA 0. For multi-GPU, it wraps with data parallel across all available devices. The output reports total time, steps per second, and time per step. The final calculation divides multi-GPU steps per second by single GPU steps per second to produce the actual speed-up ratio on your machine. Run this before committing to a long training job, and you'll know whether your setup is performing as expected or whether something in your configuration is leaving performance on the table. On 2 Tesla P40s, here's what to expect from this benchmark. Single GPU should land around 1.2 steps per second. Data parallel should reach roughly 2.0 steps per second, a 1.7 times speedup. DDP, when configured correctly with the glue backend, should hit around 2.5 steps per second, a 2.1 times speedup. If your numbers are significantly below these, the troubleshooting steps from earlier in this lesson are where to look. If you're at or above these numbers, your setup is working as designed. Multi-GPU training checklist. Before starting any serious multi-GPU training run, work through this checklist. Confirm both GPUs are detected by PyTorch with device underscore count SHE returning 2. Verify both are in TCC mode. Without it, Windows display driver interference can stall computer tasks. Check that CUDA underscore visible underscore devices is either unset or explicitly set to 0, 1. On the code side, your model is wrapped with either data parallel or distributed data parallel. Your per device batch size accounts for both GPUs. Don't use the same value you'd use for single GPU without considering the effective batch size. Data loader workers are set to at least 4 to prevent data loading from bottlenecking GPU utilization. During training, monitor NVIDIA DASMI and confirm both GPUs are above 80% utilization with comparable memory usage. Watch your loss curve. It should decrease smoothly. Multi-GPU training doesn't change the math of gradient descent, so if your loss behaves strangely, the issue is almost always batch size or learning rate, not the parallelism itself. Key takeaways. Here's the mental model to carry forward. Data parallel is one line of code, works reliably on Windows, and gets you to about 1.7 times single GPU speed. DDP is more involved, requires working around NCCL on Windows by using the glue backend, but delivers around 2.1 times speedup when configured correctly. Either way, doubling your effective batch size is part of the deal. Account for that in your learning rate. Monitor both GPUs during training. Utilization above 80% on both devices is your confirmation that everything is working. And critically, multi-GPU training doesn't affect model quality. The gradients average out to the same result. You're just getting there faster, roughly half the wall clock time. What's next? Both GPUs are now in the game. The next frontier is teaching your model not just what good outputs look like, but how to prefer them over bad ones. That's the domain of alignment. And the next lesson covers direct reference optimization, or DPO, which is one of the most powerful techniques for shaping model behavior after initial fine-tuning. Additional resources. For deeper reading, the PyTorch data parallel documentation covers the single process multi-GPU model in detail. The PyTorch DDP tutorial walks through the multi-process setup with working examples. The Unsloth multi-GPU docs cover library-specific considerations. And the PyTorch distributed training guide is the authoritative reference if you want to understand what's happening under the hood during all reduce. Your training time just got cut in half. That's real leverage on every experiment you run from here forward. This diagram shows data parallelism in action across 4 GPUs. The full training dataset enters at the top and gets divided into 4 equal shards. Each GPU receives 25% of the data for that step. Critically, every GPU holds a complete copy of the model. They're not sharing layers, they're each running the full model on different data simultaneously. After each GPU completes its forward and backward pass, the all reduce operation kicks in. This averages the gradients from all 4 GPUs and distributes the result back to every device. Every GPU then applies the same gradient update, so all 4 model copies stay perfectly synchronized. This is the core insight of data parallelism. Identical models, different data, synchronized updates. The more GPUs you add, the more data you process per step, and the faster your model converges in wall clock time. Model parallelism takes a fundamentally different approach than data parallelism. Rather than giving each GPU a full copy of the model, you split the model itself across GPUs by layer. In this 4 GPU example, GPU 0 handles layers 1 through 8, GPU 1 takes layers 9 through 16, GPU 2 runs layers 17 through 24, and GPU 3 executes the final layers 25 through 32 to produce the output logits. The data flows sequentially through the GPUs. Input tokens enter GPU 0, the activations pass to GPU 1, then GPU 2, then GPU 3. This sequential dependency is both the strength and the weakness of model parallelism. The strength: you can train models that are too large to fit on any single GPU. The weakness: GPUs spend time waiting for the previous stage to finish rather than computing in parallel. For your 2 P40s with 24 GB each, data parallelism is almost always the better choice. But if you ever work with a model too large for a single card, model parallelism is the tool. Tensor parallelism operates at a finer granularity than either data or model parallelism. Rather than splitting data or splitting layers, it splits the computation within a single layer across GPUs. In this attention head example, the 32 attention heads are divided into 4 groups of 8. GPU 0 computes heads 0 through 7, GPU 1 handles heads 8 through 15, and so on, each operating on a 1024-dimensional slice. After the attention computation, an all-gather operation recombines the results from all GPUs before passing them to the feed-forward network. The FFN is replicated across all GPUs, similar to data parallelism. Tensor parallelism is most valuable for very large models where individual layers don't fit on a single GPU. For fine-tuning with LoRa on your P40s, you're unlikely to need it, but understanding it clarifies why different parallelism strategies exist. Each one targets a different bottleneck: data volume, model size, or individual layer size. This comparison puts the major multi-GPU strategies side by side across 3 dimensions: memory usage per GPU, training speedup, and setup complexity. The pattern is instructive. DDP delivers strong speedup with full memory usage per GPU. Each device holds a complete model copy. It's the right choice for single-node multi-GPU setups like yours. FSDP, fully sharded data parallel, reduces per GPU memory by sharding model parameters across devices, but introduces communication overhead that limits speedup. It becomes attractive when your model is too large for DDP's full copy approach. DeepSpeed 03 pushes memory efficiency further and shines in multi-node configurations, multiple machines each with multiple GPUs. Pipeline and tensor parallel strategies trade off differently depending on whether your bottleneck is layer size or attention head size. For your 2P40S, running fine-tuning with LoRa, DDP, or data parallel covers your needs. These other strategies become relevant as you scale to larger models or more hardware. DeepSpeed Zero technology is a memory optimization framework that operates in stages, each one partitioning more of the training state across GPUs. Understanding the stages helps you choose the right level for your workload. 00 is the baseline. No partitioning, no memory savings, just a reference point. 01 partitions optimizer states across GPUs, delivering roughly 4 times the VRAM savings with minimal communication overhead. This is appropriate for small multi-GPU runs where memory isn't critically constrained. 02 adds gradient partitioning on top of optimizer state partitioning, about 8 times savings with moderate communication overhead. This is the most common choice for multi-GPU fine-tuning. 03 partitions everything: optimizer states, gradients, and model parameters. The VRAM savings are dramatic, up to 64 times, but communication overhead is high. This is the tool for models in the 70 billion parameter range that simply won't fit otherwise. Zero Infinity extends 03 by offloading to CPU RAM or NVMe storage, enabling models that exceed total GPU memory. For your P40 setup running LoRa fine-tuning, 02 is likely the ceiling of what you'd need, but knowing the full progression helps you reason about scaling. This diagram shows the gradient synchronization flow that makes DDP work. Each GPU independently runs its forward pass, computing predictions from its data shard, then runs its backward pass to compute gradients. These two steps happen in parallel across all GPUs with no coordination required. The coordination happens at the all-reduce step. Once all GPUs have their gradients, all-reduce averages them across all devices and distributes the result back to every GPU simultaneously. Every GPU then applies the same gradient update to its model copy. The models stay synchronized not by sharing state continuously, but by agreeing on the same update at the end of each step. This is why DDP scales so efficiently. The GPUs are independent during the expensive compute phases and only communicate briefly during gradient sync. The all-reduce operation is highly optimized. On Linux with NCCL, it uses direct GPU to GPU transfers over NVLink or PCIe. On Windows with Glue, it routes through CPU memory, which is why the speedup is slightly lower than the theoretical maximum. This memory breakdown across 3 parallelism strategies reveals why each one exists. All examples use 4 GPUs with 24 gigabytes each. With data parallelism, 58% of each GPU's memory goes to storing the full model. Parameters, optimizer states, and gradients all live on every device. The remaining memory handles activations and the current batch. This is straightforward but memory intensive per GPU. Tensor parallelism distributes the model components more dynamically. Activations consume 17% and gradients 6%, with the model itself split across devices. The memory profile is more balanced because no single GPU holds the complete model. 03 achieves the most aggressive optimization. Only 12% of memory per GPU goes to parameters because the model is sharded across all 4 devices. The remaining memory is available for larger batches or longer sequences. For your 2P40S running LoRa fine-tuning, data parallelism's memory profile is completely workable. LoRa adapters are a tiny fraction of total model size, so the full model copy overhead is manageable. These alternative strategies become compelling when you're working with unquantized models in the 13 billion parameter range or larger.